Introduce this the past couple days because I spent a little bit too much time talking about Mr. Kramer's awful revenue. So I was so much in pain from playing basketball with the guys at Grace the day before. They had like no. So I'm a small group leader at Grace with junior high and junior high school kickoff where they had just everybody was just doing games and stuff in the gym, and they like lowered their hoops and played slam ball. Well, I took an awful knee right to the quad. Like I just probably the worst dead leg I've ever had in my life. I did. I don't know who I did. Okay, so we talked yesterday about solutions. Specifically, what? What was it yesterday that we were talking about when we were discussing solutions? What was the kind of big, we talked about vapor pressure and its impact on, or how a solute impacts the vapor pressure. What was the big takeaway of what a solute is going to do to the vapor pressure?
It's going to lower it.
It's going to lower it, okay? If you have a pure solvent versus a solution, the solution's vapor pressure is always going to be lower if you dissolve a non-volatile solute. And if you remember, the reasoning behind that was because essentially what you're doing is you're replacing things that are volatile with things that aren't volatile. So the amount of particles per unit volume that you have that can actually evaporate and produce vapor pressure is smaller. Okay? So therefore, you're going to have a lower vapor pressure. Okay? We also know from previously learned stuff that the vapor pressure has an impact on a few things. Okay? The number one thing you probably should be coming to your mind would be what? What is the number one thing? What was that? Boiling point. Okay? Because we talked about boiling happens when what?
The atmospheric pressure equals the vapor.
Okay, when the vapor pressure is equal to the atmospheric pressure, it now can boil. Okay, so if a solution is going to have a lower vapor pressure than some pure solvent, what would you say is going to happen to the solution's boiling point relative to your pure substance? What?
So the solution has a...
So we talked about yesterday how a solution has a lower vapor pressure, right? Than the pure, like if I had...
Because there's less.
So if I had just pure H2O versus an H2O solution, we said this is going to have lower vapor pressure, correct? Okay? So it's going to have a higher boiling point, because if it's got a lower vapor pressure, it's going to take a higher temperature to get the vapor pressure and the atmospheric pressure to be equal for boiling to occur. Okay? And so, I kind of get a little ahead of myself. I talked about this yesterday. We talked about it quite a bit last year. It's this idea that when you're dealing with solutions, it doesn't really matter what the identity is or what the solute particle is. All that matters is how many of the solute particles you have dissolved. It's going to inhibit the volume and therefore how much vapor pressure you're going to have. Okay? And this is why it was important, because there's a distinction you have to make between ionic and covalent. What was it?
Ionic breaks apart.
Mm-hmm. So ionic breaks apart more. Okay, covalent isn't going to break apart at all. And so since ionic breaks apart more, it's going to break up into more particles, so it's going to have a significantly greater impact on the vapor pressure going down, and therefore boiling point and other things changing. So this isn't a familiar equation, isn't an unfamiliar equation, excuse me. You have seen this before, I assume. Look familiar? Okay. So that's going to be how much your boiling point is elevated. So if I say a water solution containing the solvent water has a boiling point of 100.42. What would be its boiling point elevation? 100.42.
Oh, but of course.
0.42. That would be your boiling, how much the boiling point got elevated. So that would be what you would put in as your change in T. Okay? So it's not just final minus initial per se, it's always going to be how much is difference between your initial, well, I guess it is final minus initial, isn't it? Okay?
It's gonna always be over 100.
What?
It's always gonna be over 100, whatever it is over 100.
Depends. If it's water, yes.
Okay.
If it's a different solvent, you'd have to know what that solvent's boiling point was. Does that make sense? Like if you're using benzene as the solvent, you would need to know benzene's original boiling point so that you could find the difference.
But wouldn't it have to give you the initial if you're gonna find it anyway?
Probably. I mean, they could probably find a way not to and still be able to figure it out. So. All right. Anything up there that I need to talk about? Okay, this is just a constant. I'll have to give it to you. And today I should be able to give you the constants for water, which is probably what you're going to be spending most of your time dealing with, and then molality we have discussed before. So let's do this problem. I know I put molality of the solute, but technically molality has both solute and solvent in it, so don't get confused. Because it's moles of solute divided by kilograms of solvent. So the reason why I put solute there is because usually we're going to be dealing with the solute, figuring out the moles of the solute. Okay, so it says a solution was prepared by dissolving 18 grams of glucose in 150 grams of water. The resulting solution was found to have a boiling point of 100.34. That should tell us something. What does that tell us?
That's our point.
Our boiling point elevation is what? Okay. Calculate the molar mass of glucose. Okay, and it says glucose is a molecular solid that is present as individual molecules in solution. What is that trying to tell you? What is that last sentence trying to hint? The opposite of that. Okay, so glucose is covalent, so it stays as individual molecules. It doesn't break up into.
So you don't multiply.
Nope. In this one, we know that we don't have to take the moles and multiply it by what it breaks up into because it won't.
So does glucose ever change, or is it always the same? The C6H12O6 is glucose.
What do you mean change?
Like, is there any other thing that's called glucose? Is there any
Not
other
that I'm aware of.
So just
I don't think so. Not like humans where you have the same name for multiple people. Okay. They didn't give you KB, so you have to just know it. I'm trying to remember off the top of my head. One of them was 5.12. I don't know if it's this one.
the answer is 180.18.
Looks like it is.
We're finding molar mass. Here you go, it's 1.9.
Okay. Now, how are we going to go about solving this problem?
Well, you need to use the moles of solute to find the molar mass.
Okay, so we need the moles. Which of these variables up here will at least help me figure out the moles? In this equation, which variable?
Molality.
We need molality, because we know molality has moles of solute in it. Okay, so that's probably our first step, is to find molality. And since we have change in T and KB, we should be able to do that relatively easily. That'll give me my molality. And remember, this is moles of solute per kilogram of solvent. Okay, getting closer. Now what should we do? You could do, doesn't matter which one you do first. You could, grams over kilograms. I'm not sure.
We'll just like get the 0.67 to mass.
You could do that. You could get moles to mass. Okay, you certainly, well, no, you probably don't want to do that. I lied. You want to isolate moles because we're solving for molar mass, correct? Okay, we already know the mass of glucose. So we have the mass of glucose, and we can isolate and find out how many moles of glucose I have. Then you should be able to find your molar mass. So we need to get rid of what variable up here, or what unit? Kilograms. How are we going to go about doing that? This is kilograms of solvent, so I need to multiply by the kilograms of solvent. Do we have the solvent mass?
Yeah.
What is it? So if I change that to kilograms, that's going to cancel out my kilograms of solvent, leaving me with my moles of solute. Okay? Then I can find molar mass by doing what?
Yeah. 18 divided by.
Wait, yeah,
I think it's like 180.12 or something actually.
180.18.
I done at the very beginning.
He said we kilovolts. It
Yeah.
did that.
yeah, can you just find the molar mass?
Yeah, if you know glucose,
So you
but
can just skip the whole problem and just.
you know, if you don't know what the unknown substance is. Yes, I mean the point is, you absolutely, if you knew it, then why would you spend all this time? But most of the time when you're doing something like this, it's some unknown that you're actually trying to find that you don't know what it is. Okay? Typically what these problems are gonna flow through is molality. If you're not solving for molality, you're gonna use it to figure out something else. Okay? So what we did is we found molality, was able to cancel out our kilograms, so we had moles, and then we used the grams to find the molar mass. Questions?
So the constant for boiling is 0.512.
Yeah, this is for water. You might want to make a note of that, because it isn't going to be, you're not going to always put that in, because if your solvent is something else, you're going to have to use a different constant, which I'm sure there's a table in your book that gives you all the constants.
Memorize the whole.
What page that's on, I don't know. Okay? So, another one of the colligative properties is freezing point depression. This is the one we kind of have talked about, how, why we throw salt on the ice on our roads and on our sidewalks is because what that does is creates a solution. Okay? A solution that lowers the freezing point of the ice. Why would that be important?
If it's not that cold, it'll melt.
Say it's -4 degrees Celsius. And ice would normally form at 0 degrees Celsius, correct? If you threw salt on it and it lowered the freezing point to -7 degrees Celsius, it would melt at -4, wouldn't it? Does that make sense? Okay? Now, I could explain why boiling point elevates and freezing point depresses, but it has to do with the vapor pressures, and I don't think it's overly that important at this point. Just remember that they're opposites. Freezing point goes down, boiling point goes up. Okay? Very similar equation. Just have a different constant. Okay?
So the 0.512 up here was the constant.
Constant for water, when the boiling point constant for water. The freezing point constant for water is 1.86? Yeah.
1.86 something else.
I don't think so.
For some reason that number seems like.
Yeah, because we've used it before. So your KB is 0.512. Your KF for water, I actually think it's a negative, but I don't know how important having the negative in there is. Okay? So it says, what mass of ethylene glycol, the main component of antifreeze, must be added to 10 liters of water to produce a solution to use in a car's radiator that freezes at negative 23.3 degrees Celsius. Whew. So, here's our equation. What do we know? What's changing T?
Negative 23.3.
The only reason why it's negative, it's actually the same number is because when does water freeze? And then KF we said was, okay? Now, what do you think we should do first here? Solve for Malloy. That's usually a pretty safe bet. You don't want me to just give you the answer on this?
I already got it.
What do you get?
12.5.
Okay. This is moles for 1 kilogram. Okay. So, it's important to be successful in these problems is to know what the units are representing. Moles of solute, kilograms of solvent. In the context of the problem, we want mass of what? Of solute, okay? So, if you can kind of think ahead, mass of solute, what of these two variables would we need to figure out mass of solute? You would want the moles of solute. So, we have to get rid of what? Kilograms, which is not quite as easy in this problem, because what didn't they give us? They didn't give us mass, but they did give us something else. They gave us density. Well, they didn't get, we'll have to use the liters too. You're not wrong with that. Okay? So, using density and the liters, you should be able to cancel out your solvent. So, 1 milliliter is 10 to the negative third kilograms. Why did I do that? Yeah, because this is in grams, and I need this to be in kilograms, right? To cancel out kilograms here. 1 gram is 10 to the negative third kilograms. You're looking at me like you're confused about that. Good?
You just combine the fact it's 1 gram per milliliter. You should combine
Yeah, this is the density. I just changed the units so that I can cancel out.
Okay, that makes sense.
Okay? Then, now that I've canceled out my kilograms, I can cancel out my milliliters by doing what? Okay, I gotta change that to milliliters, but that's going to be 10,000 milliliters, over 1. That's gonna cancel out your milliliters. Okay? That'll leave me with my moles. Uh, 125 moles of ethylene glycol that I would need to get the freezing point to depress this much in a volume of 10 liters. And I would finish by doing what?
Divided by 6.1. Sorry.
That should give you what you need here.
7,762.5. That's a lot.
7.76 times 10 to the third. Is that correct? Yeah. Grams of ethylene glycol. Those fun organic compound names to pronounce.
What was that? Biology test? Or botany test?
Got it? Questions? Similar, kind of similar from the previous problem, a little bit different. Okay? It's that they didn't give us kilograms, so we had to indirectly cancel out kilograms by going through both the density and the volume. Last one. Now notice we haven't come across anything that is ionic. Because when it's ionic, you have to multiply by the number of particles it breaks up into. And I actually don't think this one is ionic either. So just maybe make yourself a note when you're doing your homework that if it's ionic, molality needs to be multiplied by how many particles it breaks up into. Right? Last one. Are we doing freezing point or what are we doing? Yep, freezing point. So we can keep that constant. Okay, a chemist is trying to identify a human hormone that controls metabolism by determining its molar mass. A sample weighing 0.546 grams was dissolved in 15 grams of benzene. Ooh, we cannot use that then. Why can't I use that?
It's not water.
Yeah, it's not water. Wow, that's funny. That number looks kind of familiar, doesn't it? I mean, it's a decimal place over, but. Okay, and it didn't say here, you probably could find it in your book somewhere, but for the sake of time, just give you what the freezing point constant is for benzene. Okay. So we're trying to find the molar mass of our particular hormone. Sounds like the first problem we did, doesn't it? First problem that we did. So without going through this whole problem, what you would probably need to do is with your depression number here, you would find molality, correct? Okay. Then from molality, you'd want to find moles of your solute, which means you'd have to get rid of kilograms of solvent. Can you do that? What would you use to cancel out kilograms of solvent? Yep, you would use your solvent mass, just change it to kilograms, right? Because benzene's your solvent, correct? That would leave you with your moles of your solute, and you would finish by doing what?
Grams of mole.
You would find M, you cancel that out, you'd be left with moles of solute, and then you take your mass divided by your moles to get your molar mass. It's exactly like the first problem we did.
What's the change in
Because it tells us that's the depression. Does that make sense? It didn't, that's not the boiling or the freezing point, new freezing point. It's saying we have no idea what the initial freezing point was, but we know that it got depressed by that much. So that would be your change in V.
But if it is water, if it's found less initial